Yeah, welcome everyone for cloud computing and big data, and welcome to the online audience as well. Today, the topic is deep learning applications in clouds. It is actually very complementary to the material we learned in lecture 6. In lecture 7, we go here and there in more details because lecture 6 was very, very quick to get you ready for assignment 2, which is essentially all about deep learning and executing it in the cloud. And here and there, we show you what other clouds exist. So how you can actually use deep learning in the cloud with different tools on the one side, and on the other side, we look a bit more on the details. We had things like convolutional layers, very quickly, strides and paddings. And I think we didn't really spend time properly to really engage in this. So before we do this, let us just review what we had the last time. So parts of lecture 6 was really starting back what we did in lecture 2, right? Beginning of the course, we had this interesting, very little learning model called perceptron, which was just one line, actually a linear learning model playing with the line with a so-called perceptron learning algorithm. And at some point in time was actually converging with a line and actually then able to create a decision boundary which basically differentiates class 1 from class 2. Admittedly, a very simple model from the 60s, but today, interesting enough, still the really core of what we call the neuron. So this round thing is loaded because this is used in all deep learning until today. Of course, on steroids and quite combined with nonlinear activation function and so forth, but the key building block is still, let's say, this little perceptron, which is now basically coming to a neuron. Really, if you extend it, when you remember, we had just the sign function to really do some, binary class decision, or we did a logistic function to then do basically some classification. Here we're talking now on linear activation functions. We put per neuron essentially so together in this, let's say, round block we defined as a neuron, and we can there be really flexible, what means nonlinear activation function. And we had the last time that this is really needed because essentially a linear learning model would be always staying linear. And with this, we could have not fancy decision boundaries. You remember the circle, for instance, we had when one class is outside the circle and another class might be inside the circle. So still with this, let's say, small, tiny block, the key idea remains the same. We have X as a data set and, our weights will be basically the ones that we learn. Now we have, of course, a hyperparameter decision more or less to switch between different, let's say, nonlinear activation functions. However, the practice is usually there are some that are standing the test of time. For deep learning, we have seen that ReLUs are actually quite often used, or leaky ReLUs, rectified linear units. But of course, it depends on the application problem sometimes. And so you can also play around with others that are actually given here. We also learned that, of course, when we want to have this MNIST character recognition, we have a problem. We don't have 2 classes anymore, right? We have to have 10 classes. And that is something where we, of course, also have to work on the model by just combining essentially 10 neurons at the same time. So this is not yet a neural network, right? It's we call that a multi-class perceptron still, because there's still not the idea really of a hidden layer, so to speak. It's just the input and output. Right? The neural network really comes with a hidden layer in between, which we see here. And the beauty was that this was relatively okay in compute time. That's why the compute blueprint is very, very low. And you see it's keep rising with the different architecture types. And this is the reason because we just had very little parameters to train, right? When you make the mass basically 10 times essentially the input dimension of this vectorized input image that we had, right? We actually, from this 2D images we had here from the numbers, we create a very long vector. We lose the spatial information. That's what I pick up today. And then we just stick it in this multi-class perceptron, having a softmax at the end that gives us then the probabilities of which class it belongs to. However, with the parameters, it was very easy to train. Still, the question was, as we got just 90%, could we do better, right? And we said, okay, let's try fully fledged neural networks, which have essentially the same principle, just add more hidden layers to the game. Instead of having the input layer directly connected to the output layer, you put neurons in between. And actually this was where machine learning stopped before doing this, because essentially you cannot train that anymore, right? That's why we said we need something like back propagation of error through these different layers in order to understand how good we are in terms of error. Here it's easy, input, output. I can always combine my output or compare my output to the input. Was it the right goal and what I get out there? When I do this here, I just get something at the end. I have no idea how I should improve essentially the hidden layers and the weights here. Hence, you propagate the error using the derivatives and chain rule, as we discussed the last time a little bit briefly, but also Rocco will go, basically my PhD student, in the next lecture a little bit more into this. The trouble with this, when you start this, you have not only to decide how many neurons you put in the hidden layers. So that's something which you have to think about, a hyperparameter. Do you want to have 128? Do you want to have 20? But this, of course, largely depends now on your computing capacity, because quickly these parameters will grow from just 8,000, we are already at 120,000 roughly. And this is, of course, cycles. So all, let's say, what we discussed before, admittedly always lists trivial computations. And hence, that's why we also can nicely use a GPU, because each inherently matrix multiplication that's happening here with the weights updates that we discussed in one of the rules is essentially not really much computing, just the sum, the whole sum of it, doing it for all the parameters is much. And that is actually also something what you will learn in assignment 2 by executing this to really understand why CPUs are very bad here and why GPUs have an order of magnitudes of margin to play. However, we reached then 95% trained over 20 epochs, also something what you can elaborate in the assignment, then maybe do 200 epochs, maybe things will change. Things like overfitting kicking in and regularization parameters will play a role. But we said essentially just putting more hidden layers maybe doesn't do the job. And this is not what we consider as deep learning, right? Deep learning always stands for an improvement in different certain architecture as well. And this is an important consideration. You have seen one particular example today. I do sequence modeling with long short-term memory and gated recurrent units a little bit just to show you it's not all image recognition. Also sequence models can do deep learning. But here the deep learning is, of course, still using the concept of a neuron. And I think this got a little bit lost the last time because we had this high-level quick view. So we dive into all of these different things in this lecture today to show you a bit how it reflects again to the neuron that's still standing. Just, of course, doing very interesting thing as a combination of doing something we call a kernel and basically a filter operation in the convolution layers. But long story short, by doing these different tricks, by having always convolutions, rectified linear units, or let's say nonlinear activation functions, then pooling, and iteratively doing this concept, you have image recognition, which is cutting edge today, essentially. So we reached 99.36% in this recognition task, which of sort was understandable because we have also seen, some of these digits were so not really visible for us humans even of it if it is a 3 or 5. So there's maybe no chance that any deep learning network could do 100%. That's what we left last time, and we used TensorFlow and Keras just as an example. There's PyTorch, there's MXNet, there are different packages outside. All of them have a unique selling proposition. So what we do today essentially, to complement this lecture, really, we look firstly how we can execute it in the clouds like AWS, for instance. But of course, the Google Collaboratory is also a very good example usually. But then also it will be complemented by my PhD student, which show you then the really big scale on Tuesday next week as an invited lecture complementary to this. So we come back to our usual problem, MNIST, and we'll look a little bit what can we actually do in terms of clouds of getting the environment, right? We want to have TensorFlow, PyTorch, MXNet, all these different packages. Is there something which we can get? In the AWS, there's some EC2 that we essentially already were alluding to when we look in Spark clusters. They also use the EC2, but now we want not to have any Spark cluster. We actually want to do this easily on a really, let's say, bare metal virtual instance. So virtualization is important for us, but still not all this kind of different Hadoop and Spark ecosystem what we had the last time. So it's a different concept. And we see that this is Amazon Machine Images. We have already lots of packages pre-deployed for machine learning, and I will make the point why that is so important. They're extremely low-level libraries that we need, and all of them need to be in the right version with the right packages to work. Otherwise, you have significant problems or really lots of time problems. So in the second part of the lecture will be more advanced concepts, where I really want to pick up of the ideas of the CNNs, again, as a very detailed example. Of course, I told you a lecture series like we have here in cloud computing cannot go into the details. So we just have one that you hopefully after this lecture will understand completely. Left alone the deep learning course that is by Magnus or so with lots of different models you can take there. I give you some sneak previews what other deep learning lectures and basically possible solutions could be existing to also image recognition like residual networks. They do skip connections every now and then, are actually very powerful. But then we also have to go the price for it and go to billions and billions of trainable parameters. And there's really where every of the little laptops end, right? So even if we have seen some coming to class and say, I run a model after 360 hours on my laptop and still could do the job. But when you have this billions of parameters, you really need the cloud or high performance computing. At the end, some neuroarchitecture search in AutoML, thinking about the architecture on the other way, that essentially architecture means we have to build it, but who says that humans are good in this? Right? So in a way, we are not good in this. And the neuroarchitecture search and AutoML principles these days in research, it's cutting edge research, or we just show a little bit where the trend goes, that we don't even take the decisions anymore as humans, right? We just gave the machine the idea to do, and then through reinforcement learning or genetic algorithms, the architecture that is needed for a classification problem will be crafted by the machine. Of course, this goes to the other end of the scale, where at some point in time we make as programmers also obsolete. And you have seen the Boston Dynamics robots and so on. So there's of course also danger in that they try to program themselves. And there can be lots of things wrong. There's of course something as a warning in this area, but still we're not that far, right? So everything what you know from Terminator that the machines take over, I think is not so easily coming in practice. Lots of showstoppers. However, if you want, I don't want to put it explicitly in my slide sets, please go to YouTube and look at Boston Dynamics. What these robots can do in creating themselves and learning themselves is remarkable these days. Good, so let's come back to our problem. I think by now everybody understands that problem by heart. It's a 10-class problem that we want to solve. So how I would do this now in the cloud? What could be potential solutions? And the one that we last time had already was, let's say, using the Google Collaboratory with TensorFlow. So could we do something similar maybe in another cloud? So in a way, we did this already and can say, yeah, checkbox, we have that done in lecture 6. So there's some Python scripts. And we know from the last time of this lecture, essentially, I would just go that way when I really know I want to do large deep learning networks. When I do still some support vector machines, random forests or so, your laptop is still fine. You would even say small neural networks are maybe just fine on a laptop. With the hidden layer, maybe just 2 and then just a couple of neurons in the hidden layers. But as soon as you come really to medium deep learning networks, something we maybe see with AlexNet, or large deep learning networks with ResNet 125 hidden layers and convolutional layers and skip connection, then you really need basically cloud computing. The benefit you get is, of course, unbeaten accuracy, as you have seen also already in the image recognition task from the characters. But if you go to a real science problem, there's, of course, a much, much larger margin. And I show you some examples and Rocco much more on Tuesday from our real research in remote sensing. So we would start essentially looking again on our key pairs. And you remember the key pairs from Amazon. That was, once you have swiped the credit card, it's the first thing you do, always to get control. So basically you create this key pair in order to access the system remotely, right? With some SSH client, basically sometimes it's also even integrated in some other, let's say, Jupyter notebook styles that you can also see when you use it in the assignments as some application called SSH. But in any way, this is the first thing that you have to do in order to get really the underlying resources right. Of course, for deep learning, we are mostly interested here, GPUs, right? That will be a key concern. And hence, we cannot, again, use AWS Educate. I mean, this is obsolete anyway, but couldn't use it before because they don't offer free GPUs to us for the assignment. That's why we also always basically already go to the Google Collaboratory for the assignments. But in theory, you could also use the Amazon AMI, and I show you how. By really starting again with the key pair generation, you have to always think about in which area you are, Virginia, and which basically part of the cloud you actually create the key pairs. They're just valid for certain areas, like we have seen in the Spark environment, right? It's the same game here. We just create the same key pair, because the underlying idea is, of course, very similar, like we had with Elastic Reduce service. The same is actually for the EC2, which is the underlying system which we're going to use, but without MapReduce this time. This time we want to just use pure virtualization. So when this key pair is created in your dashboard, you have now the chance of basically then searching for basically new services and so on. And one of these are these interesting instances from virtualization that you learned already in lecture 4 in virtualization. So there are some pre-configured images that we can launch and instantiate, right, using virtualization. So someone has done the work for us to put a VM, a virtual machine image, installing all this deep learning packages for us. And when this image is there, we can use it. We also learned in one of the courses that the versioning is the hardest thing in this. So when you go there, no wonder you will see there are lots of different versions. And just as an example, what packages exist here, I mean, by now that's something what you all already know, so I can basically go here a little bit more quicker. These are 2 packages, but when you go to the whole list, I want to make some connection. Now this is a bit hard visible and this particular beautiful beamer, but at least online in the recording, you will see a little bit the differences. So here's an MXNet packages in a very specific version, and TensorFlow in terms of version 2.3. There was also long time TensorFlow 1, and these already have some incompatibility issues. So if you have some script based on Keras, based on a very old version of TensorFlow, it will not work. The other way around as well. When you use cutting edge TensorFlow, but an very old TensorFlow script will also not work. So meaning that these all in a way have to stick together. There are some exceptions. There's some PyTorch, which stands alone a little bit. And MXNet and TensorFlow and PyTorch could be seen on the same level, right? They're all different packages that you're going to use for neural networks and all have their different offs. And also Rocco will make some connections. So the interesting thing, however, now for this image is if you go one level deeper, it has also something like Nickel and Intel libraries, which are specifically, let's say, tuned for deep learning. And they are installed in these images as well. They again have to match in a layered hierarchy, so to speak, to all the deep learning packages again. And there's cuDNN, which is cuDNN, a specific version just for NVIDIA GPUs. And as we see now, Radeon and many other accelerators coming along. As I told you last time, we have now contact with GraphCore, the company. So we're looking already in research on CPUs based on a graph design, right, for AI, because many of the problems you have in AI are actually graph-based. Also TensorFlow, if you look in the heart of it, it actually transforms all what you do in Python to a large directed acyclic graph again in order to compute. But anyway, this is more, let's say, research cutting edge. But the key message to take away is it's a really hard exercise, and Rocco will tell you this in the next lecture, to always keep these different systems and versions under your control, on yourself, up to date. So an administrator has a very hard work to do this. Hence the motivation to just go to the cloud and use virtualization. They have already several of those. You see also traditional virtual machines just with an operating system. We actually learned in lecture 4, SUSE, Red Hat, Windows. But here we're not interested in just an operating system. Here we want to have a specific Linux, which is actually not something we care about that much. It's just one Linux, one Unix derivative. We care much more that all these difficult, let's say, deep learning package versions are ready for us deployed, and we can be sure they work together. So when just clicking this and launching this, you immediately know there's always some side remark in clouds. I have to pay for everything, and you have to pick now exactly which instance type this virtualization should be based on. So what is the really physical hardware underneath that to support this? And there are different versions. Of course, here when you launch it, you don't have the pricing, right? So that is kind of intentionally kept just on websites. That makes you easier to choose, but you have to always think what it really means in terms of getting the costs here. And it varies, of course, you see from a couple of, not even cents per hour for a very little CPU up to cutting edge CPUs where you already pay, $2.4 an hour or so. This is just for CPUs, but remember for deep learning, what we want to do is, of course, using cutting edge GPUs. And with this, we need much more computing power and much more pricing because then we also are talking about $24 per hour, roughly, for a cutting edge GPU. And then it can be costly very quickly. Again, apologizing for the beamer here. I maybe should talk to them to get a bit better one for this. But you have at least the recording to have as a backup. Once you review this and basically can launch it, you will see immediately a problem of the free tier. So that was also part of the educate package, that GPUs are not allowed. It's always a warning there. So that's why we cannot really also use it properly in the assignment, because you also should explore the difference between CPU and GPUs. What happens is basically out of the snapshots from these images, which are prepared in some elastic block storage that we will actually see in lecture 8 very soon, what exactly that means, but some data storage, the image is lying there. You basically register this AMI and can then basically launch one. You can even copy one. Basically, it's this virtualization concept that we already know. We can do our own snapshots, put everything to disk and reload again, and so forth. We get live migration and all the benefits of virtualization directly gratis. Now, it is very complicated in a way, in my understanding, by using AWS. So basically, MS Azure, if they wouldn't have stopped the other HD Insight and so on, is much more easier integrated to use Jupyter, for instance. Yeah, so I think still the cloud users in AWS have something to do, but they also offer you different products, and I come to this in a moment. They want you to promote also SageMaker, which is an end-to-end solution on a complete different level. Here we're talking more or less infrastructure as a service. This will come in lecture 8, lecture 9, lecture 10 now, what these abbreviations mean. But essentially you have just Metal, a virtualization layer, and your deep learning packages. So the usability is admittedly not really nice, and if you want then to really connect to it, you have to do some exercises. You see it on the slides later with your secure shell, logging in. And once you're logged in, you basically see at least that all the packages here are installed. You see here essentially MXNet in different versions, TensorFlow in different versions, all what would be available to you. And there's some specific strings which are very important because it gives you the connection string to Jupyter. Still, it's not like as we have seen with Spark and so on in MS Azure, one click and then start Jupyter. Here we really have to do lots of exercises to really get, let's say, Jupyter somehow nicely integrated. And we had this at one time also as an assignment, and we stopped that because it was really, let's say, not the usability point of view for the cloud course. But think about that. This is, of course, prepared in a company now from administrators, which are usually working on this infrastructure as a service level. You see here a kind of rerouting between different ports and IP addresses. You have your key in a specific type and version connected to this compute cloud EC2 instance in order to make things work. And once you're there, you can essentially, through port forwarding and some special tricks, use the browser as you would use it basically locally in order to use Jupyter. So you can already see it is working. It's nice, but still we had also often when we're trying that quite some problems. But of course, then once you have done this, you have a remarkable option of kernels. And this is something where, behind every Jupyter instance, Jupyter notebook are these kernels which demand now to say what is the different Python versions, MX versions, Chainer. I was talking about this recently, so it's something for reinforcement learning. I used once PyTorch, TensorFlows, and always in this different package, let's say, version, so that you can keep track exactly what are the underlying libraries with what package. And this is, of course, important when you have large scripts that you don't want to change and update all the time. Let's say if you have something else in MNIST, of course, you have your application problem. You don't want to update always these scripts. So maybe sometimes you want to preserve backwards compatibility by using just old kernels, and still it would work in the AWS and this AMI because they use the power of virtualization, supporting, let's say, also older versions of your script, at least for some while, basically, which is one of the benefits definitively in AWS in this regard. While the usability is really questionable in my opinion in a way, but you see also why they're doing this in a moment, because this is really the infrastructure as a service. So there are lots of issues with sometimes being, dead, if someone just clicks on the Jupyter and it will die, and just like a normal browser window, instead of stopping the kernel and, really doing a proper reboot, then the connection is lost. There are lots of showstoppers in between, which are very technical, and I want to stop talking much about it. But if you try it, it's quite challenging to do it. Of course, then the solution that comes along from Amazon directly is, why not make it easier, right, for the machine learning expert? And here you go. They provide, in the meantime, something called Amazon SageMaker, which is on the SAAS level. So it's on the complete different idea of scale, right? We have infrastructure as a service, just basically hardware and a little bit of virtualization, platform as a service with a couple of packages prepared. And then software as a service is really just software like, like Google Docs or whatever, Google Maps. It's just here and there. Of course, here you have to swipe the credit card for it in order to build your whole pipelines of machine learning. Now, the beautiful element is that for machine learning in the free trial, there's some hours, of course, available, and quite some, there's 250 hours. And with this, it's basically accessible. And with this, of course, people get hooked to this environment. It's relatively simple to use. It's built on top of very different EIS and PAAS services from Amazon directly. So it's a product of Amazon itself, so to speak, and making it, of course, quite clean, nice. The problem is, of course, once it's 250 hours are over in the free tier, you kind of hooked, have all your pipelines built into this particular software application. And with this, you cannot just simply quickly go away to PyTorch or some other vendor. So you kind of locked in this vendor lock approach. And this is, of course, very common for SaaS applications. You have customer relationship management systems. We will talk in lecture 10, where this is, of course, common practice. Once you're locked into these systems, you cannot get really all your customers out to get it just to another one, because it's part of the principle, right? To get the customers locked into the silos. And with this, keeping, customers paying. The key benefit, of course, is you avoid all of this time-consuming manual installation again. Or basically, as I said, the AMI image is still, in my perspective, not really fully usable, like compared to HD Insight and other tool sets I have seen. But yeah, I think in a way, they also motivate you to really, don't waste time with AMI and images, just go directly to our SaaS solutions. And I think this is a common trend in cloud computing everywhere. Everybody's striving to make it easier. Nowadays, people in the iPhone don't have an idea what a file is, right? Basically, you just have apps, Spotify, there's something running, fantastic. So people these days really lose the connection with the physical environment, with the physical backbone completely. And this is, of course, then also contributed to, again, also having this kind of vendor lock problem that you have with this, which is, I think, the most hardest one, because with this, once you're trapped in this, they can demand, so to speak, any price, right? They can high up the prices and there's nothing what you can do so quickly to get out of it. SAP is also partly known for it, right? So if you use SAP for, your customers, for your sailing system, whatever, once you have all your data in, it's very hard to do data out. That's what they charge, right? The interface to get data out or to get data in another system is where they got lots of money from. They want to keep you as customer. So much for blaming. As a university professor, you can always have this freedom of neutral, honest broker of saying the truth here and there, and also as a warning message for you when you go to companies. Before you really jump on SaaS, always think about it, that maybe it would be better to hire here and there an administrator that knows the details and can configure these things. Of course, if you have many different users and you have a very good return of investment, maybe then Amazon would be, let's say, another choice in terms of using the SaaS solutions as an example. You can go also to other vendors, of course, Google Proc, we will look in lecture 9 as well. Right, so basically in the next 5 minutes, I give you this video. I didn't find a shorter one to really finish the first part, which gives you several options how to do it in the cloud now. All of them share a little bit this ideas on the different layers. Hence, from next week, Thursday, we talk about the different layers: infrastructure as a service, platform as a service, and software as a service. Here with the Google Cloud Platform, we a kind of PAAS level, so platform as a service, but you see also Google actually jumping tremendously towards software as a service, while actually infrastructure as a service is mostly still Amazon that is providing there the most elements. So let's have a look on this video. And then we get more into details of deep learning networks again. Just a good overview, I think, so that you also get an expression that not everything is in Amazon, but also some things are actually in the Google Cloud. And the Google Cloud is different from the collaboratory, right? Just that you know. He will tell more about it.
A sense of Google Cloud Platform machine learning products in just a few minutes? Let's find out. Despite all the attention lately, machine learning still remains somewhat difficult to build, maintain, and deploy. Thankfully for you, Google Cloud Platform puts a lot of that behind the scenes, so you don't have to worry about it. So what does the hello world of ML look like when you don't have to write the neural nets yourself? Simply calling the Vision API to describe what it finds in the picture. As a leader in machine learning, Google Cloud offers several high-quality pre-trained models via APIs that can easily be consumed by developers regardless of the language they use or the nature of their application. Developers can invoke the API directly or using one of the idiomatic client libraries available in numerous programming languages. Here, we invoke the API directly from the product description page. From this image, the API can detect a broad set of labels, provide dominant colors and other image properties. It can also extract text, identify entities such as landmarks, celebrities, logos, or news events along millions of entities that it supports. It can also moderate content, such as all of your app's user-generated content. In addition to the Vision API, GCP offers pre-trained models for text-to-speech, speech-to-text, natural language, translate, all via easy-to-use APIs. Now, pre-trained models are amazingly easy to use, as we've seen, but they're not trained on your set of data. This is where Cloud AutoML comes in. Cloud AutoML is here to enable developers with limited machine learning expertise to train high-quality models specific to their business needs by leveraging Google's state-of-the-art transfer learning and neural architecture search technology. Cloud AutoML provides a simple graphical user interface for you to train, evaluate, improve, and deploy models based on your own data. You're only a few minutes away from your own custom machine learning model. Now, the ML APIs and Cloud AutoML are great when you want to use or build upon a pre-trained model that Google already has training for. But what if your needs are beyond that? Well, that basically requires training your own models with your own datasets on your own virtual machines. And I don't know about you, but I don't always have time for that, which is why I use Cloud Deep Learning VM Image. These Google Compute Engine instances come pre-installed with the latest versions of TensorFlow, PyTorch, and scikit-learn. You can also add Cloud TPU and GPU support with a single click. This image also comes with the latest software drivers and third-party dependencies, including the latest GPU software, and is available using the GCP Marketplace from the console or using the command line. If you'd like to get the operations out of the way and focus on your models, consider using Cloud AI Platform, which offers fully managed training and prediction services for developers and data scientists. You can build your models with multiple ML frameworks, including scikit-learn, XGBoost, Keras, and of course TensorFlow. Cloud AI Platform trains any model at large scale on a managed cluster. Hypertune is a unique feature that enables you to reach better results faster by automatically tuning deep learning hyperparameters. Cloud AI Platform then offers online predictions adjusting to any request rate coming from your ML-enabled applications, and does so through a secure web endpoint. Batch predictions are also supported for really cost-effective inference from asynchronous apps. Whether you're new to machine learning or you're already an expert, GCP has a variety of tools to help you, from pre-trained ML models accessible via simple API call, to customizing models with AutoML, to training and serving a custom TensorFlow model using Compute Engine or Cloud AI platform. Consider taking free code labs linked in the description below to explore these products. Check out the Compute and Big Data Overview episodes and look forward to an upcoming video on big data storage and processing. Please like, subscribe, comment, and share. See you.
Yeah, thank you very much. I think we have seen enough. Short disclaimer as usual is I'm not paid by those, but you have seen that they're actually going, of course, in the same market segment like Amazon, right? So same tools. What is particularly interesting is here you have seen Cloud Vision APIs, natural language processing APIs. So this pre-trained models, which makes up this platform, is quite interesting. So we will talk in lecture 9 more about it to really understand what the platform character is and where they maybe have a bit more unique selling proposition. But more and more in the last 5 years, you see that when Amazon does a service, Google does a service, and Microsoft does the same service. So they kind of are all equal, and Alibaba not to mention. Of course, they do very similar things. So in this sense, I think that's all what I needed to leave here on the table for the first part of the lecture. And we break here for 10 minutes before we come to the second part.